Section 7. How might global warming affect your community? Digging deeper. Effects of global warming in your community. Problems with making predictions. In the Investigate, you used what you explored earlier in the chapter to make predictions. You predicted the effects of higher global temperatures on your community. You also designed an investigation or model that could be used to test your ideas. In this Digging Deeper, you will read about some of the problems that scientists face as they try to predict climate. Many scientists believe that Earth's climate is becoming warmer due to the greenhouse gases humans add to the atmosphere. These gases are carbon dioxide, methane, and nitrogen oxide compounds. Throughout geologic time, Earth's climate has naturally gone through warmer and colder phases. Therefore, it is hard to say if average global temperature has been increasing only due to human activity. Currently, remote sensing of the land and ocean surface by satellites makes it easy to obtain a good estimate of global temperature. The problem is that such techniques did not exist in the past. As a result, climatologists have to rely on conventional weather records from weather stations. That poses problems. Thermometers change. The locations of the weather stations often have to be changed. The move is usually away from city centers. As urban areas have been developed, they become warmer. This is due to the addition of pavement and the removal of cooling vegetation. This is called the urban heat island effect. Climatologists try to make corrections for these effects. The consensus is that global average temperature really is increasing. This raises several questions. How much of the warming is caused by humankind? How much is natural? It is known that there have been large variations in global temperature. They have taken place on scales of decades, centuries, and millennia for quite some time. This has been the case since long before humankind was releasing large quantities of carbon dioxide into the atmosphere. Scientists who study global warming use very complex computer models to predict what might happen. These models do not simply look at carbon dioxide and global temperature. They also do calculations based on many other factors that might be involved in climate change. There are a wide variety of factors. For example, the factors include how much moisture is held in Earth's soils, as well as the rate at which plants transpire or give off water vapor. The physics of clouds is an especially important and uncertain factor. The workings of Earth's atmosphere are still much more complex than any computer model. Scientists try to address this by including a mathematical expression for each process that affects the atmosphere. This involves asking questions about what happens to climate. For example, what if the oceans become warmer at higher latitudes, or what if there is more rainfall in subpolar regions? Climate models must take into account the effect on global temperatures of the oceans, the land, as well as the biosphere. Climatologists are always trying to improve their models so that they take into account as many factors as possible. Drawbacks to computer models. As you have seen, many factors influence the climate on Earth. These include carbon dioxide and other greenhouse gases, Milankovitch cycles, and ocean currents. The positions of continents, weathering of rocks, and volcanic activity also influence the climate on Earth. Many of these factors interact with each other. Scientists do not fully understand all of these interactions. This makes it hard to accurately predict how the atmosphere will respond to any one change. The ways that different factors interact in global climate change are called feedback loops. Feedback may be positive or negative. Positive feedback occurs when two factors operate together. Their effects add up. For example, as the climate cools, ice sheets grow larger. Ice reflects a greater proportion of the sun's radiation. This causes Earth to absorb less heat. This results in Earth becoming cooler, which leads to more ice forming. Ice cover and global cooling have a positive feedback relationship. In a negative feedback relationship, two factors operate in opposition with each other. Each tends to counteract the effects of the other. One example of a negative feedback pair is weathering and carbon dioxide. Weathering uses up carbon dioxide. This causes the temperature to drop. When the temperature drops, weathering rates slow down. Less carbon dioxide is used. This slows the rate of temperature decrease. In this sense, weathering acts as a negative feedback for global cooling. Earth's global climate involves many feedback loops like these. Understanding of such feedback loops is very crucial in understanding how Earth's physical environment changes through time. How many feedback loops are there? How do they work? These are questions that scientists are working on every day. Some loops are more powerful than others. They can also vary in rate and last for different lengths of time. The uncertainty about feedback loops is one thing that makes it hard to predict how Earth's climate might respond to an increase in carbon dioxide. Another major unknown is global warming. Another major unknown in global warming is clouds. With warmer temperatures, there will be more evaporation. Therefore, there will be more clouds. Clouds reflect incoming solar radiation into space. This has a cooling effect, but clouds also act like a blanket to trap and hold in heat. This has a warming effect. Which effect predominates? Scientists are still not sure. What do the computer models say? Scientists continue working on their computer models of global climate. They learn as they go and make improvements all the time. Some of the models have been used for years. Therefore, scientists can test some of the predictions of past years against weather data collected recently. This helps them refine the computer models to make them work better. Computer models have come up with some possible scenarios. These scenarios may result from the increased amount of greenhouse gases in the atmosphere. Remember that they are theoretical. They are not certainties. Changes in precipitation. Warmer temperatures lead to more clouds. More clouds lead to more rain. Some models predict more rain with climate change resulting from a warmer global climate. Others predict a change in rainfall patterns. For example, they predict more precipitation in the winter and less in the summer. Some areas of the world would receive more rain than others. With the increase in evaporation brought on by warmer temperatures, an increase in extreme events, stronger hurricanes, and winter snowstorms might be likely. Changes in sea level. Glaciers around the world have been shrinking in recent years. If Earth's climate continues to warm, more and more glacial ice sheets will melt. Meltwater is returned to the ocean. This would result in a worldwide rise in sea levels. Some models predict a sea level rise of as much as a meter by 2100. Changes in ocean circulation. Warmer temperatures could lead to the melting of glaciers. This fresh meltwater could disturb the production of North Atlantic deep water. Recall from Section 3 that the same thing happened 12,000 years ago. The flow of North Atlantic deep water helps distribute heat from solar radiation evenly around the globe. If this flow is disturbed, there might be far-reaching effects on global climate. Changes in agriculture. Most of the world's cropland is located in the northern hemisphere. Warmer temperatures would cause a northward shift of the regions where certain crops are grown. Agriculture would also be affected by changes in rainfall patterns. Some regions might become too dry to support present crops. Other places might become too wet to support present crops. Many areas might continue growing traditional crops. However, the productivity decreases. In other words, farmers might still grow corn in Iowa, but produce fewer bushels per year. An example of a change that might decrease crop productivity is an increase in nighttime temperatures. Corn and some other grain crops do best when the temperature drops below 70 degrees Fahrenheit at night. Another change that could reduce productivity or increase costs is a switch to wetter winters and drier summers.